Hello everyone. Myself Rishabh More, and I'm a final year PhD student in Purdue University, and I'm working with Professor Arzu Ardekani. First of all, I would like to thank the organizers for such a wonderful uh, mini symposium, and also all the speakers for like nice talks. So today I'll be talking about effect of stratification and fluid and inertia on the dynamics of a single swimmer or the interaction uh, between a pair of swimmers. So to start with, if we look at the upper layer in oceans, uh, these are home to plenty of organisms whose like size ranges from a few micrometers uh, to a few millimeters, or in some cases like big fishes and whales, they are like a few meters long. So as a result, their Reynolds number also ranges from zero, where we have viscous dominated regime, to a few hundreds where we have inertia dominated regime. And most of these organisms, they reside in this upper layer where we have plenty of sunlight and plenty of nutrition. uh, and and if we focus mainly on phytoplanktons and zooplanktons and other small scale organisms, they basically come in a different variety of shapes, sizes, and they use different mechanisms to move. And one such mechanism is the presence of cilia, an array of cilia on their surfaces. Um, so for this talk, I'll be using this ciliary kind of motion as a model. And another important characteristic of this upper layer is the presence of vertical density gradient. It can be due to the presence of vertical temperature gradient, or salinity gradient, or a mix of both. So it becomes important to see how this stratification and also the inertia, it affects the motion of these organisms in these upper layers. Uh, so um, it has been seen that there are these large scale phytoplankton and algal blooms, which scale like a few kilometers horizontally, and also the dial vertical migration of these microorganisms, where they routinely have to cross this stratification barrier to reach this nutrient rich regime. So so the questions that I'll be try to answer is what might be the possible mechanisms behind these blooms, and horizontal accumulation of these organisms, and how stratification will affect this dial vertical migration of these organisms. So the choice of model for the swimmer is something called a Squirmer model, and uh, this in this model the microorganism moves by the presence of this oscillatory surface velocity field on its surface, and depending on the ratio of these two constants b2 by b1, which is called beta, we can um, classify them as pullers or pushers. So a positive beta is a puller, negative beta is a pusher. And if even if we look closely at the flow field around these organisms, so for a pusher, it seems like the pusher is trying to push the fluid around it, in front and behind it, so that it can propel forward. And on the other hand, a puller seems like it is pulling the liquid which is behind and in front of it to its side, so that it can move forward. And this model has been used a lot throughout the years to model the motion of organisms and study various um, phenomena, such as their swimming speed in Newtonian or non-Newtonian fluids, the nutrient uptake by these organisms, also the interactions between a pair of organisms in a homogeneous fluid at uh, various Reynolds number, also to study mixing by swimmers in oceans, uh, dynamics and rheology of swimmer suspensions, also the um, inertial effects on their swimming. And finally, this has also been used previously for studying stratification effects. So this is a continuation of all these studies. Um, yeah, so the governing equations are simple. They are Navier-Stokes equations and advection convection equation for the density. And we assume these swimmers to be neutrally buoyant and assume that their density changes as they move, so that it matches with the background density. And the important dimensionless parameters here are Reynolds number, uh, which gives us the importance of inertia, Froude number. I'll mostly be using Richardson number, which is a combination of Reynolds and Froude's number. So Richardson number is a measure of fluid stratification, and Prandtl number. So yeah, so before going on to the results, let's just look at what will happen if we first increase the inertia of the swimmer. So these blue arrows, they show the velocity field induced by the swimmers near their bodies at a previous time step, which is this solid body. So let's say at a later time step, somehow this swimmer gets perturbed from this original straight line motion. Then you can see the flow field uh, induced by a puller at a previous time step. It tries to further push this puller away from the center line. So as we increase inertia, a puller becomes unstable in the sense that it strays away from the straight line motion. But on the other hand, for a pusher, the effect is completely opposite, and it is pulled towards the straight line. So it is always stable even at higher inertia. But now if we have, so this was in a homogeneous fluid, but now if we include fluid stratification, then this, as as you can see, the puller, it tries to pull this heavier fluid into a lighter fluid. So actually the effect of then, because of buoyancy, this pulled packet of fluid, it tries to goes to its original position. So the effect of stratification is basically to oppose this uh, this perturbation in the flow field by the swimmer. So it's the same for a pusher as well. So stratification, basically it tries to stabilize a puller while it tries to destabilize a pusher, which is shown by these representative arrows here. So as we increase the effect of stratification, uh, a puller becomes stable, and a pusher, it might become unstable. And since the effect of stratification is to oppose the flow field induced by the swimmers, we can expect the swimmers to slow down. So that's exactly what we see from our simulation results, where these plots show the swimming velocity of swimmers normalized by their swimming velocity in a homogeneous fluid at the same given Reynolds numbers. So for both pushers and pullers, we observe that their swimming speed, it decreases inversely with the Richardson number or stratification. So this has also been observed experimentally, where here the small s means weak stratification, and a capital S means a strong stratification. So as we increase the stratification, they have seen that the vertical descent speeds of these organisms, it decreases significantly, and that's the reason why. So as the swimmers, they move and they encounter this stratification layer, their speed actually decreases significantly, and as a result, they, if the stratification is strong enough, they cannot penetrate this layer and get uh, stuck here, and that might lead to their accumulation. Again, so as I mentioned, puller is it becomes unstable as we increase its Reynolds number. So this is for Reynolds number 50, and this blue curve is a homogeneous case. So they basically stray away from their straight line trajectory and even get deflected in the horizontal plane. But as we increase the stratification, as you can see, a puller becomes stable even at this high inertia. And a pusher is eternally stable in a homogeneous fluid, even if we increase its inertia. But then as we increase stratification, its swimming speed decreases, and at a high enough stratification, it again strays away from the straight line trajectory and becomes unstable because of the strong stratification effects. And this is depicted nicely in this animation. So a puller in a weak stratification or a homogeneous fluid, it becomes unstable, while in a strong stratification, it is stable and follows a straight line path, and the effect is opposite for a puller. And we also came up with this nice phase diagram uh, uh, where the open symbols here show the stable cases, and the closed and the filled symbols are unstable cases. So as you can see, for a puller, which is the lower half, um, as we basically increase the stratification, it becomes stable, which is divided by this dashed line. While on the other hand, for a pusher, as we increase the stratification, it might become unstable at very high stratification strengths. And moving forward, another reason to why this happens, the stability of these swimmers, it changes, can be um, found by looking at these vorticity bubbles. So as the puller swims, it has this vorticity bubble behind it at high Reynolds numbers, while for a pusher, that vorticity bubble is in front. So as we increase inertia, this vorticity bubble, the size of this vorticity bubble increases for a puller, which basically obstructs the convection of vorticity downstream, and that's the reason it becomes unstable. But now as we increase stratification, you can see the size of this vorticity bubble, it's reducing, and as a result, the vorticity can convect easily downstream, and hence it becomes stable. But on the other hand, for a pusher, the vorticity bubble is in front, and as you can see, its size increases drastically as we increase the stratification, and this again provides obstruction for the vorticity convection and makes it unstable. And moving forward, if we look at two swimmers, they are moving opposite each other and colliding. So pullers, they have these closed loop trajectories in a homogeneous fluid, and they get trapped near each other. But if we have a strong stratification, then actually they don't get trapped near each other, but collide and get separated from each other with the angle of separation it reducing with increasing the stratification. But for a pusher, it gets separated in a homogeneous fluid, but as we increase the stratification, it after a strong enough stratification, they collide, and they kind of stick together and get deflected in this horizontal plane, and that's basically related to the instability of each individual pusher at high stratification. Another important parameter to look at is the contact time of these swimmers as they collide in a stratified fluid. So with increasing stratification, we see that for both pushers and pullers, the contact time increases significantly. So this indicates that stratification might help these organisms if they are reproducing sexually. It might help them to spend more time near each other and can increase their chance of their success. So to conclude, the important parameters are Reynolds number and Richardson number, which tell us the importance of inertia and stratification. So if we have, let's say, pushers and pullers of two different sizes, and they're trying to swim in these upper layers, so since they are like neutrally buoyant, whether they are swimming down or swimming up, it does not matter. So if they are small in size, then that means their Reynolds number is very small, and they are actually stable, and they can basically pass this stratification layer here. But if we increase their size, then a puller, so if we increase their size, they see the effects of stratification more strongly, and their velocity reduces drastically, and also they can become unstable, which might lead to their trapping in this horizontal layer, and which might then lead to their accumulation. So the combined effect of inertia and stratification is that on the stability is that inertia tries to destabilize a puller, but stratification stabilizes, and inertia stabilizes a pusher, but stratification destabilizes it. And yeah, so stratification increases the contact time, and also it reduces the swimming speed, and which might lead to trapping of bigger organisms, which has also been observed previously. So yeah, that's it, and I'd be happy to take any questions. Thank you.
Yeah, so first, that's really perfect timing. So
yeah,
yeah, let's first thank our speaker. Okay, so any question? If you have a question, you can just yeah, so either raise your hand in chat, or you can just unmute yourself. I think
sorry, may I
there's.
ask so I don't know how to raise hand when you are co-host. May I ask a question? So stratified stratification, the fluids, is it anisotropic? Does it have preferred direction?
Yeah, it is actually vertical. It is in the direction of gravity. So yeah, it is vertical.
And how does it enter the stress tensor?
So it does not enter the stress tensor. So actually, so if you look at the governing equations, yeah, so we basically use Boussinesq approximation. So we assume that the perturbations or variations in density are only important in this body force term. So the stress, it depends on the, so it might enter in the pressure. So the hydrostatic component will change around the swimmer because the density is varying, but this but it enters this flow field kind of indirectly. So it's like not a direct relation between stress and the density variation.
So stratification just force terms.
Yeah.
Okay,
pressure and basically the body force.
Thank you.
There's actually one question in the chat. Maybe you want to read it. From Kirsty 1. Which organisms induce puller-pusher flow fields at finite Reynolds number?
So there are like there are examples of bacteria and paramecia. So there are some paramecia they have these ciliary organs on their surface. So there are a few examples with their with their size. The Reynolds number becomes important. I don't and also this Squirmer model is useful for volvox actually, which is kind of a spear and also has the ciliary organs on its surface. So in some cases, depending on the viscosity of the fluid, its Reynolds number can also become important.
Kirsty, if you want, you can just unmute yourself and ask the question.
I guess thanks for the answer. Maybe I think in for ciliates and volvox, it's still very small.
Yes, yeah.
Even, I mean, you can't really reduce the viscosity, right?
Right.
It's already water. So maybe, I guess some other phytoplankton.
Yeah, so actually, yeah, the Squirmer model is kind of for zero Reynolds number, but recently researchers are trying to extend it to like higher Reynolds number and just use it as a model and see what will happen if we have finite inertia as well, which might be the case in some special cases.
Okay, thank you.
Any other question?
I have a quick question, if I may. So, Rishabh, I think you said you basically match the swimmer's density to its environment locally.
Right. Yeah.
So typically organisms have a slight density difference with their environment, right? I mean, it's maybe on the order of maybe 20, 30, 50 kilograms per meter cube.
Yes.
What do you think might happen when you account for that?
Yeah. So this model is, so actually there are some organisms which can do this and transfer with their surroundings, and they can change their density so that it matches, but it's not true for all the organisms, as you mentioned. So if that is the case, then they will have a density difference with the surrounding fluid, right? So depending on whether locally that density is higher or lower, there will be an extra buoyancy force on them. So if locally their density is, let's say, higher than that horizontal level, then there will be extra force on them which is in the downward direction, and they will sink. But if their density is smaller, then the buoyancy will be in upward direction and they will rise. Until they actually come to a level where their density is equal to the surrounding fluid, and that is called the neutrally buoyant level, and they will basically start to decelerate as they come closer to the neutrally buoyant level, and finally stop there, unless they have some mechanism to propel them.
Thank you.
Okay, so yeah, so if you have more questions, so you can type in chat, and so for speaker, so yeah, so right now we need to move on to the second talk.
Thank you.
Thank you. Yeah, let's thank again to Moore. Hi. Okay, so yeah, Dr. Moore.